Hello, hi everyone. Welcome to lab session 2 of hardware software co-design. In this lab, we'll be looking at VGG 11. We looked at the architecture of VGG in our lecture 2, and we'll be looking at pruning. This is what we had done in lecture 4. So let's begin. You can actually go to the GitHub repo. I'll just show you. You can go over to the repositories. And here you will see the lab session 2 IPython notebook. You can download this and upload on your Google Colab notebook and you'll be good to go. So in this lab session of hardware software co-design, we will explore the steps involved in optimizing a deep neural network for efficient deployment on hardware platforms. Specifically, we'll focus on VGG 11, which is a popular convolution neural network, and the primary objectives would be divided into three. We'll understand the basics of deep neural network training using VGG 11, and we'll use a CFAR10 dataset. Then we'll learn how to prune a trained model to reduce size and computational complexity while maintaining the accuracy, and we'll analyze the performance trade-offs associated with the pruning techniques. So we'll go through the training of VGG11 model, pruning, and then we'll fine-tune the prune model. Obviously, these steps are not like exactly the steps which I mentioned below, which you'll see later on. And this is how it is structured: an introduction, then model training, model pruning, fine-tuning, and then performance analysis and conclusion. So by the end of this lab, students will gain hands-on experience in optimizing deep learning models for deployment on hardware platforms. And they will learn to balance accuracy and efficiency, a critical aspect of hardware software co-design for AI applications. So in this step, we will prepare the CFAR10 dataset and apply some data augmentation techniques such as random cropping and horizontal flipping. We will also visualize some samples from the dataset to understand what our model will be trained on. These things, are random cropping and horizontal flipping, are used to randomize the data more so that the machine learning model can train better. So with these commands, we have imported the PyTorch, the datasets, the data loader, and the matplotlib. We've figured out that the GPU is properly available to our system, and we'll define the data augmentation and transformation things, the random crop and horizontal flipping. We'll load the train data set and the test data set, and we'll visualize some images from the data set by this code. This is for like the samples which are, we'll just pick up samples in this range, and this is how we'll show it using the matplotlib. So you can see we have taken airplane, automobiles, bird, cats, deers, dog, frog, horse, ship, and trucks, and there's examples of all these images in the data set. Then we'll define the VGG model. This is the step 2. We'll define the VGG 11 model architecture. So the VGG 11 model is a type of a convolution neural network which is widely used in image classification tasks, and it consists of series of convolution layers followed by fully connected layers. And the model uses filters of size 3 cross 3 with a stride of 1 and uses max pooling layers to reduce the spatial dimensions. All this we have studied in the theory lectures of lecture 2 onwards. And the final layer is a softmax layer for the ultimate classification. For those of you who do not remember, I'll just pull up this slide where we had studied. So you've seen that we had studied the architecture of VGG 16 and saw the convolutional layers with 3 cross 3 kernels and padding layer of 1 with some with stride of 1, and then max pooling layers in between these convolutional layers, and finally linearly connected layers. And each of these convolution layers is a combination of convolution, batch normalization, and passing through a ReLU layer. Let's get back. So this is what we've tried to define the VGG 11 model here. We're forming a sequential layer first with convolution layer 1. So we've already learned previously that if we pass the neural network through this convolution 2D network, and this 3 indicates here the number of input channels, in this case since this is a starting, so it will be RGB, the 3 channels, and this represents the output. So the output of this layer will definitely go into the input of this layer. And we're defining the kernel size and the padding. We're also implementing ReLU. ReLU is the rectified linear unit, which is an activation function which introduces non-linearity into the systems, which helps us capture complex patterns. Passing in place equal to true helps optimize the memory consumption because it does not create a copy, it does the operation there and then itself. So similarly, this is a repeating structure which we have used to make the VGG 11 model. So if you remember from the diagram how the VGG 16 got its number, so we had seen that there were 16 layers to this, 16 convolution layers and the linear layers together. So here also if you count, we have 8 convolution layers and 3 fully connected layers, so therefore it makes this VGG 11. This comes under the modern deep learning models, and therefore it's not straightforward, but still it's easy to understand. Finally, we're defining the forward function, and we're instantiating the model by passing the number of classes as 10 because we have the CFAR 10 data set, and we're printing the model. So once we print the model, this is what summary we'll get. To extract the features, this is what we are getting. It's mentioning all the things, the stride, the padding, the kernel size. And for the sequential, for the classified layers, we have linear, which tells the in features, out features, the leaky unit which is in place, the dropouts, again the in features which matches the out features from the previous layer, out features defined from here, and finally the out features coming as 10. Each mapping, each giving a probability of what is the probability that this particular image belongs to any of these 10 classes. So once we've created the model, now is the time to train the model. So in this step, we will train the VGG 11 model on the CFAR 10 dataset. Training a model involves feeding the input data through the network and calculating the loss and adjusting the model parameters using backpropagation. We will here use cross entropy loss as our loss function and Adam optimizer, and we'll see the training and validation loss and accuracy over epochs. So again, we've done the importing and we're setting the device to be used as CUDA if torch.CUDA is available, which will default to yes, it is available. So we'll move the device model to the device by passing this model.to device. We'll define the hyperparameters, the learning rate as 0.001, batch size like 64 images will go at once, and there are 10 epochs which we're defining. And we're defining the data loaders, train loader, test loader, and defining the optimizer and the loss function, which is cross entropy loss. And this is the code for training. So in this, we're just defining the function. We'll call it later. We'll call this function later here by train model, where we'll pass the model, the criteria for training, the optimizer, train loader, test loader, epochs, and the device which you want to train on. And it will come inside this function. So here we'll store the training loss and the training accuracies, the validation loss and the validation accuracies in a list. And for each epoch, we'll perform this loop. This is for showing the progress bar when the training is happening. And this is the actual training loop, which will perform the back propagation also, and will keep on updating the progress bar with the current running loss and the loader. Finally, we'll compute training loss and accuracy for that epoch, and we'll do the validation loop and compute validation loss accuracy. And this is how we'll train the model. Finally, we'll get the training loss, validation loss, training accuracy, and validation accuracies after the 10 epochs, and we'll plot all of these things like these arrays, these lists which you have defined over the epochs. We'll print that using matplotlib. So here is how the training summary is. The device got selected as CUDA because the GPU was available. And for the first epoch, the training loss was 2.407, the accuracy was 19.25%, the validation was 1.7, loss was 1.7, and validation accuracy was 31.53. So you can see that as we reach high, like more epochs, the training loss is decreasing, the accuracy is increasing, and the validation accuracy is also increasing. And this we've plotted over epochs. So if you would have continued for more epochs, this would have gotten better. Uh, So sometimes what happens, like when I had previously performed, so because of certain factors like the learning rate which I had chosen and the model initialization was not proper, so I was getting very poor results and the training and validation loss was stuck at around 2.3 and accuracy was nearly 10%. So basically indicating that my model wasn't training at all, it was the random guessing for a 10 class classification problem like CFAR 10, I was getting accuracy of 10%. So many of you might get it because because of the hyperparameters which you have chosen, it might get stuck. So it might not be every time, but it might get stuck. So for that, there are certain things which we had changed. We had adjusted the learning rate, tried lowering it down. We had normalized the data before passing it. So we had updated the transform function. We had not just done the random cropping, horizontal flipping, but also normalized the data. And we tried a different optimizer other than Adam, which is known as SGD, and we also initialized the model weights again properly. So with this, once we ran this loop, we saw that the accuracy increased much faster and reached 74.63% by tuning the hyperparameters and other things. So now comes the model pruning. So model pruning is a technique to reduce the size of neural network by removing less important weights, and pruning helps in reducing the computational cost and memory footprint, making the model more efficient for deployment in resource constrained environments. So in this step, we perform unstructured pruning on VGG level. So we'll, we'll, uh, we'll import the utility from torch itself, known as the torch.nn.utils.prune. We can implement it from scratch, but we leave it onto another session or another time. We're right now learning the torch utility for pruning. We'll do a deep copy of the model, and in this model we'll prune. So there are two kinds of pruning which they have: the unstructured pruning. So here we pass in the module, which is basically the name modules which we're capturing here, name comma module, and the amount by which you want to prune. So here we're pruning the network directly by 50%, which is quite an aggressive step. But by passing this to 50%, we'll prune the weights in an unstructured way. Unstructured way basically means that the weights that are close to zero in a particular layer, we'll remove them. And after evaluating the model, we see that the accuracy, pruned model accuracy was 71.4%, which dropped like from 74.63 to 71.4 naturally. So now we would want to actually, you see that the pruned model accuracy previously when I ran it was around 69.41, right now it is 71%. So this decrease is expected due to the removal of substantial number of weights, and such a reduction in accuracy is common after pruning, particularly with high pruning ratio, which we have chosen like 50%. So the original model size was around these many parameters. You can see it's around 28 million parameters, and after we've pruned by 50%, close to 14 million parameters. So the results are what are expected, and is approximately the half the original parameter count. Rest all the parameters are made to zero, and but by again fine tuning the model with the data set which we've already chosen, we can again recalibrate the remaining weights to perform better. So this is what we'll do in this fine tuning step, that we'll again train the model by providing the data set, and this time you'll see that fine tuning epoch the accuracy was raised to 83%. And why did this happen is because the lesser the number of weights, the more the gradients would be, and with only 5 epochs you were able to reach 83%. Here also, if in the original model, if you would have trained for more epochs, you would have reached close to 90%, but we did not continue for that long. So ultimately the accuracy was around 82%, suggesting that the model might be approaching its optimal performance after pruning and fine tuning. So that is it for this lab. Try to follow along and try to understand the concepts in this. Thank you so much.